Okay, welcome everybody. Let's go ahead and start with the Mamdani projects. Last time we had Sam Cullen and Ming Kun who made presentations. So I guess we have Innocent and Matthew and I guess and Trevor, right? Yeah, I guess so. So who would like to go first? Innocent, are you ready to talk about what you did?
Yeah, sure, I can go first.
Okay, let me allow you to share screens and go ahead and show us the great stuff that you did. Keep it concise, of course, because we want to minimize our time. So go ahead and share your screen if you'd like.
I'm doing just that. Okay. So I hope my screen is up now, right?
Yes, we can see it. Thank you.
Okay. So right here is just the Simulink block diagram of the system that I used to simulate the project. So for the car, I just used a simple integrator, which you can see right here. Then this other bus is the fuzzy logic block. So for the fuzzy logic block, you have two inputs into it. You have the error and the change in the error. Then it goes into the Mandami control, then gives the pedal out what the pedal output should be, whether it should be some kind of an acceleration or deceleration. But in my case, I wrote it as a brake, like applying the brake on the pedal. So yeah. Then right here, we have the antecedent and membership functions. We have that of the error, and the first one is that of the error, and the second is that of the change in error. For the error, I decided to go with the Gaussian membership function. Then, but for the point where the error is 0, I decided, since this point is kind of a well-known point to be 0, I made use of a triangular membership function for it. As you can see right here in the top, at the middle, you have a triangular membership function, but the rest is a Gaussian. Then, but for the change in error, I made use of a triangular membership function for all of them.
So let me ask you this, if you could go back. All of your triangles are not the same interval. Why? Did you try a bunch of stuff, or was this, it looks like you maybe used the fuzzy membership toolbox or the fuzzy logic toolbox. Is there a reason that you chose the triangles in your other antecedent not to be the same width?
Yeah, I did that because at this point I'm kind of dealing with the change in error. So I was like, I'm more focused to make sure that I walk towards 0.
Okay.
Points, yeah. So for the pedal output, which is the consequent membership function, I made use of a triangular. We have this right here, ranging from -4 to 4. So in the negative region, you have, that means you're applying the brake. As you can see here, you have the applying a big brake, medium brake, small brake. Then when it's 0, you're doing nothing. Then right here towards the right, you have small acceleration, medium acceleration, and big acceleration. So the next is the fuzzy rules that were generated using the membership function that I had, where you have on the top here, you have the error, and this column right here, you have the change in error from big negative to big positive. Then right here, you see what the output should be, what the consequence should be. Then, in order for me to get the range for this, because right here you can see that the error I made it to range from -40 kind of to 40.
So that means that -40 means you're going backwards, right?
Yeah, that means the error is going in the opposite direction. Yeah, kind of the error is decreasing.
Okay, let's see. I guess I'm confused. Oh, this is the error that you're talking about, the error membership functions. Okay, go ahead.
The error, yeah. So in order to figure out a good range of operation for the error, so I did a test of when it was ranged from -60 to 60 and when it was ranged from -40 to 40. Then when I did that, what I observed is that if you tend to like increase the range of this error, it kind of increases this should be the rise time for the system, because when it was -60 to 60, you can see the rise time goes all the way to 8 seconds. But when it was -40, it was just 4 seconds. Then the same thing, the same test was done for the change in error for -10 to 10 and -6 to 6. Then looking at this, you can see that reducing the range of the change in error kind of increases the settling time. As you can see for here, when it was from -10 to 10, you had a settling time of just 2 seconds, from 4 to 6 seconds, which is 2 seconds. But when it was -6 to 6, it was like 6 to around 8, which is an extra 2 seconds. So with this, I had to like go with the design that I have here for it to be -10 to 10 and -40 to 40. Then
Okay.
what else? Another thing that I try to do is to play around with different differentiation methods, because what I used above was the centroid. So over here, I tried the bisector to see the kind of results I will get. So right here is the result I got with the bisector. But when I tried the mean of maximum, this is what I got.
Huh.
Yeah. So next is just showing the surface map for the bisector and the norm. So this is what their surface map looks like.
Okay.
For the two of them. Then another test that I did is kind of to like change the target speed to like a variant target speed that varies from 30 to 90, all the way down to 20 to 10, all the way back to 70, then down to 50, to see how the system I designed will be able to track the target speed. So right here, you can see that I did a good job in doing that, though the system looks to be more like a critically damped system. But something worth pointing out is that if you kind of zoom into this area where it kind of reached the target speed, you will notice that the system is having a little bit of an oscillation at that point, going up and down around about the target speed. So, but the difference is not something a control designer should be concerned about.
Do we see that? Oh, there. Okay. You've zoomed in on the oscillation. Interesting.
Yeah. So this is for the error, how the error changed and the change in error. Then this is the pedal position. So right here, you can see what I'm saying. You can see that the pedal position you didn't get a point where you have like a constant pedal position. It was just going up at a very small range between along and 0.
This reminds me of what happens when you change too quickly, right? If you've taken a control theory class, have you heard of the idea of bang bang control? I think that this is kind of bang bang control. So, okay, go ahead. Interesting.
So this is the end of the presentation. Yeah.
Okay, and you have to translate that last word for us here, Innocent.
It's also thank you. That's in my own native language.
Okay, great. Well, thank you very much. Okay, wonderful. Yeah, go ahead and unshare your screen then. Yeah, it turns out the bang bang control is what happens when you adjust too quickly. If you think, for example, of control of your thermostat, if you set it at a certain point and say you had the heat on, and all of a sudden it begins to cool off. As soon as it cools off a little bit, the heat goes on and it goes up. Then it gets too hot and it turns off and it goes down, and you get bang, 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 bang as the heat turns off and on. And of course, the way you get around that is the phenomena of hysteresis. Specifically, you do not set a specific threshold. Rather, you set an interval. And if you notice, like in the summer, I noticed the room's getting a little warm, and then the air conditioner kicks on. And the reason for that is because the hysteresis in the thermostat goes up and it hits the upper threshold. Then it cools down to where it hits the lower threshold. And by that, you smooth out things quite a bit. So it looks like, Innocent, that you were getting this kind of bang bang control. Really interesting. Very good. Okay, let's see. Matthew, do you want to take a shot, or are you ready? If you're not ready, that's okay too. Okay, you are ready.
So I did not use the fuzzy control toolbox. In retrospect, I probably should have, because what I have does not converge. So I used just straight up MATLAB, just raw coding.
Okay, well, good for you. That's the way that true adults do it, right?
Right, it's over. Can you still see my screen?
Yes, we can see your screen. Yes.
All right. So I define my error variables. Here's a linguistic descriptor, and I've also made membership functions for each of these. I'm using this Gauss membership function.
Sure.
This Gaussian. And I'm just defining, I adjusted these a little bit. This is the standard deviation. And then this is the mean, where it's centered at. Here is, I plot these down here. So you can see that this is just some normal input. This is the difference in speeds, the current speed minus the other speed, and these are the membership functions that describe it. It says way too slow, just right, too fast, way too fast. And as you can see, these go off to 1. It's a piecewise type thing. And so then we go down. I also defined the delta.
Matthew, let's not go through the code. Let's kind of stick with graphics and stuff if we could,
right?
Because I don't know about you guys. I look at code and it makes me sleepy. So
here's the delta feedback error function. So
okay, I don't see your screen changing for some reason.
Let me just try sharing again.
Okay. I think you're changing your screen and I'm not seeing it changing. That's the reason I thought you were reading off code, because nothing was changing.
Gotcha.
Okay, now, yeah. Okay, now it's scrolling. Okay, thank you.
Wonderful. Okay, so here's the input errors, current speed minus target speed. Here's the delta, so our change in that error. Here's membership functions that describe it. Of course, -0, positive, didn't get too fancy there. And then I also have, these could have used a bit more adjustment, though I don't think this was a problem. Here's several definitions for the output membership functions. Again, they go off to 1 in either direction. And we have small values here to make up for if there's wind resistance or something like that. And so I made a, let me go to the spot. So on the left here, if the table looks like this, the rules matrix.
Sure.
On the left, the columns is the error, and on the, or sorry, the rows is the error, and the columns is the delta error, so the change in error. And on the right, you can see how I wrote those out. So if we're going way too slow and the change in error is negative, we're going even slower, it's pedal to the metal. And it goes all the way out there. So I imagine you can piece together what that means.
Okay. Has everybody noticed that these rule matrices are often diagonal,
Mhm.
that the rules kind of go diagonally up, which is kind of interesting and is a feature that you could use to decrease the computational overhead. If you're really interested in speed, if your speed of what you're doing isn't fast enough, you can take advantage of that structure. Anyway, that's a matrix which is referred to as, if it goes diagonal from upper left to bottom right, each of the diagonals is called a Toplets matrix, and that's a special type of matrix. Anyway, it is interesting that most of these rule matrices are indeed diagonal. Go ahead, Matthew.
That's very cool. And maybe something's wrong with my rules matrix, which is means it's not converging. Getting here. This is just code defining loops, etc.
Sure.
I start off with a target speed of 10. Calculate error. So error starts off at 10 or negative 10, but it's absolute value, so it doesn't matter. I define a delta time. And then this is my current loop. Every iteration in this loop, I recalculate. I take the input and recalculate the output. And
okay, so it doesn't work, you say, huh?
Right. So the acceleration converges, but it's not the right value.
It converges to a negative acceleration. You're always applying the brakes.
Yeah, which is not correct.
Weird. Yeah.
Here's the error. As you can see, the error keeps increasing and the speed keeps going down, down, down.
Okay. Well, keep plugging at it. And if you get a solution, let us know. Okay.
Gotcha.
I mean, it's, yeah, it's hard to know it's hard to help you without detailed analysis of what's going on, but
right.
You get an A for effort. So, and plus you did not take the easy road of using the MATLAB toolbox. So good for you, Matthew.
Can I ask you a question?
Okay. Yeah. Well, let's ask everybody. Okay.
Right. I'll ask. So I'm following the structure where I take the sum, I calculate this grid. Say if I have a value, I say if I have an error value and a delta error value, right? And I plug it into all the membership functions of this grid. And so that gives me a grid of values. And then I sum all those membership functions and take the centroid of that. And that's supposed to give me my target speed. Am I just missing anything obvious?
Well, you're computing your target speed and your acceleration, aren't you?
I'm sorry. What do you mean computing the target speed?
Yes. The
the
acceleration should eventually go to zero, as we've seen on some of the other examples.
Yeah, I see what you mean. Here okay. I'm adjusting the speed by just like integration against the accelerator.
Uh-huh.
And here I'm picking that accelerator based off of the centroid of the weighted membership functions of that table. So
okay. Well, I tell you what, Matthew, I don't think we should take our time here in trying to finding out bug codes, but
right.
Does anybody see anything obvious at all? Okay, well, let's go ahead and finish up. And then if you get this working, let me know, okay?
Thank you.
Okay, appreciate it. Okay, this leaves Trevor.
Okay, let me share my screen. All right, so starting off, I've got the antecedent error membership function. So just calculating the speed error. I had it set so that the very large negative value was 10, the negative value is 5. And then, or it just goes up by intervals of 5 for the large negative, the negative, the 0, the positive, and the large positive.
Okay.
And then I kept the same intervals for the delta error as well. I saw that when I had different triangle widths for the delta error value, my cruise control was kind of just doing a heartbeat motion above the or around the target speed. And so after
Now,
taking
heartbeat, do you mean it was oscillating?
yes, it was oscillating around the target speed and never even met the target speed. And I'll show an example of that.
By the way, do we think that if we waited a little bit longer between updates that it might work better?
I tried, I did ones and then like 1 second and then 5 seconds and 10 seconds. And I still saw the same thing. So I don't know if the intervals need to be longer than that to see any lack of oscillation.
Okay, go ahead. Go ahead.
So that ended up with a very similar table to what we've seen before. With the, as Dr. Marks mentioned, the diagonal of zeros across the table, and then is following with the changes in acceleration from small positives and small negatives to positives and large. So small positives I had, or small positives and small negatives, I just had a change of 1 for the accelerations. For the positive and negative, I had 3. And for the large positive and the large negative, I had a change in acceleration equal to 5.
Okay, go ahead and move on then, Trevor.
So then with a higher target speed than my current speed, I noticed that it kind of shot like about 10 miles per hour over the target speed, sat there for a second, and then decreased before reaching the target speed. And
This is the only example we've seen so far of overshoot. We've seen critically damped and overdamped. I suspect overdamped sort of solutions, but this is the first one we've seen overshoot, right?
Mhm.
Okay, interesting. Go ahead.
And so I thought it was a little interesting how it overshot and then settled. So I wanted to test with a lower target speed compared to the current speed. And that's where we saw more of the oscillation around the target speed.
Bang, bang.
Yes. So just swapping the target and current speeds from 60 and 90 respectively, we notice oscillations between 59 and 62 as it goes with a target speed of 60.
By the way, if you reduce this to practice, we'll see this in neural network training, by the way. We'll see this kind of oscillation. Remember it because it does appear in neural networks too. But I think that in maybe the actual implementation, if this switching is relatively fast, you're not going to see that because of the momentum of the car. Just a thought. The momentum of the car is inherently going to smooth this out because the car, because of its mass, is not going to be able to change the velocity this quickly. Otherwise, you would sit there in a vibrator, I guess, right? Okay. Okay, go ahead.
That's the end of it. Just showing a higher target speed compared to current speed, and then a lower target speed compared to current speed.
Okay, so you got to that result, but with a lot of lip flubbing,
Yeah.
sort of thing. Okay, great. Thank you, Trevor. Okay, great. Thank you guys. Thank you guys for doing that. And please drop off your stuff in box. And it'll be nice if each assignment like this one you put in a little folder where you can include your code and you can include your PowerPoint slides also. So I wanted to continue. Any questions or comments on the fuzzy Mandami control? I want you to know that we did no Laplace transforms, no PID. PID, by the way, is suboptimal anyway. It just works well in a lot of cases. But it did okay for fuzzy control. And that's the reason, because of the simplicity of this, that it was used and adapted in things like washing machines and dishwashers. And shoot, in Japan, they applied it to everything. They applied it to rug warmers. You know, you walk across the floor and your rug gets warm. They applied it to rice cookers, all sorts of things. Any place you need a control, they can do that, and they have done that. Okay, so let me go ahead and go back to the kind of overview of search, and let's kind of review what we've done. We've had the idea of the inherent difficulty of a problem, of a search problem. If you're looking for something, there is an inherent difficulty of it, and that is something that we refer to as the endogenous information. And that's the log base 2 of the probability of guessing the correct result on the first query if you have no information about anything that's going on. And we looked at various instantiations of that, and looked at cases where we could indeed measure the active information. So I want to go back and I want to finish this. This is something that we'll be able to finish today. Let's see, where's my full screen? Right here. Okay. Okay, full screen. We did the stepping stone information from the last time. By the way, I've put these PowerPoint slides in the spreadsheet. So if you want access to them, you're certainly welcome to download it. Okay. Now, a lot of the problems we've looked at thus far are, it's kind of obvious that active information is being added, but there are cases in domain expertise, very simple cases, where the choice of active information and the domain expertise, if you will, is less obvious. And one that we're going to look at now is probably something that you've already seen at the Cracker Barrel restaurants, and that's the Cracker Barrel puzzle. The idea of the Cracker Barrel puzzle, of course, is that you want to jump these pegs. And for example, down here, peg 1 can jump peg 2, and then you remove peg 2. Or we could have 9 or 10 jumping 9 and we remove 9. Or we could have 14 jump 9 and remove 9 also. So we have 3 possibilities. So if we know nothing about the game, when confronted with this, we would say, first of all, we have 3 possible places that we can go. And what we're going to do by applying Bernoulli's principle of insufficient reason is to assign a probability of 1/3 to each of those jumps. Which one of those jumps is better? I don't know. And that's the idea behind totally blind search. You don't know. You don't know what is going to be the best. The game ends when there is no more, when there are no more moves to be made. And you can see here that there is no peg that can jump another peg and stay on the board. So this is a finished game right here. This is a finished game. And so we can go to the top here, and that is the that's the overall puzzle. You're said to win the game if after your last move, you have 1 peg remaining on the board. So in the last move, you have 1 peg remaining on the board, then you move. So if you want to know a winning combination, here it is. If you memorize it and go into Cracker Barrel next time with your relatives, you can you can impress everybody by winning the Cracker Barrel puzzle, and then sitting back and slyly saying, "Oh, that was easy." Okay, so this is a winning sequence of moves. So the question is, what is the difficulty of this problem? What is the difficulty of winning the Cracker Barrel puzzle? Now, you have a couple of things going for you. First of all, you get to choose which one of these positions is initially open. So you can have the middle position open, you can have a corner open, whatever. And then you have all of these different ambiguities of moves. The one up here, for example, we said that we had 3 possible moves. Sometimes you might have 2 possible moves. Sometimes you might only have 1 possible move. When you have no possible moves, the game is won. So it turns out that I calculated the endogenous information of this was 7.4 bits. Now, how would you compute or estimate the endogenous information? How would you estimate the endogenous information or calculate it of the Cracker Barrel puzzle? The way you do it is, go ahead.
Well, would you be taking you'd want the number of possible combinations of moves, right? So are we talking about moves or just configurations?
We want the probability of winning under the assumption of Bernoulli's insufficient principle of insufficient reason, which means that if we have more than one possibilities, we flip a coin and we choose one of them randomly. I'll tell you the simple way to do it. If there are certain things you can calculate, like if you roll a die, it's immediately obvious that the probability of getting 3 pips are the little dots in the die, the probability of getting 3 pips is 1 out of 6, right? That's obvious. But what if I ask you the question, if you play the game of Monopoly, what is the probability after 15 moves that you end up on free parking? Now, after 15 moves, you have all sorts of weird stuff going on. Remember, if you roll doubles, you get another turn. You have to figure that out. You have to figure out what happens if you land on chance or community chest, and it tells you to go to a place, right? All of that stuff has to be figured out. And I tell you what, figuring that out analytically is very difficult. So one way that it can be done is something called Monte Carlo simulation. Monte Carlo was invented by the genius von Neumann. And maybe some of you have heard of von Neumann. Early on in the Manhattan Project, he had to compute some probabilities, and they were just too difficult to compute analytically. So he wrote a computer program and just did a bunch of trials on the computer program, looked at the number of successes, and in the end, he says, well, you know, the probability of the number of successes is about equal to my number of successes divided by my trials. For example, if you didn't know that 3 pips was 1 out of 6, you could apply the frequency, the Monte Carlo situation, and you could roll a die 1,000,000 times. And if you rolled a die 1,000,000 times, you would find out that approximately 1/6 of them, not exactly 1/6, but approximately 1/6 of the time that it came out with 3 pips. And you could take that experimental result and you could figure out that probability if you weren't smart enough to figure it out in your head beforehand. The same thing about landing on free parking after 15 turns at Monopoly. That's just really rough to do. But suppose you wrote a computer program and you analyze that computer program, you task that computer program to play the game of Monopoly and go for 15 turns and see how many times you ended up on free parking, right? And if you played that 1,000,000 times, well, the number of times that you ended up on free parking would be an estimate of the probability. Does that make sense? So that is Monte Carlo simulation. So the way that this 7.4 bits was computed was the game of the Cracker Barrel game was programmed. A random peg was removed because one of the pegs has to be removed, right? And it's 1 out of 15. So you removed 1 out of those 15. Then on each case, you analyzed the number of jumps. You flipped a coin, or you can't flip a coin for a chance of 1 out of 3, but you understand you applied at every point Bernoulli's principle and just took equal probabilities which one to take. And you ran this 1,000,000 times. And after you've ran it 1,000,000 times, you see how many times that you won, that you ended up with 1 peg. So that's the Monte Carlo approach. And the Monte Carlo approach is, as you can see, very powerful. And you might be using it in your research. It's used quite a bit for very difficult problems that require probabilistic analysis that defy straightforward number crunching. So that's what happened. this was generated, gosh, I forget, a few million times. And it turns out that you can see here that the estimate after that 1 million times was 1 chance in 169. So the probability of success was 1 over 169. And if you take this, remember, we're taking probabilities and making them into informations by taking the log. So if you take the minus log base 2 of that, that's about equal to 7.4 bits. Now, again, I like bits because that tells me more intuitively what the probability is. It's the probability of flipping a fair coin and get 7.5 heads in a row. And so immediately I know what 7.4 bits is because I can relate it to the probability of coin flips. So a guy comes along, and this is the endogenous information. This is the I omega. This is the 7.4 bits. So a guy comes along, and you don't know this guy, but he says, you know what? When you have a choice, don't jump into a corner. All the action takes place in the middle of the game. And if you jump in the corner, chances are you might get isolated there. That's what he tells you. Now, is that good advice or bad advice? Maybe you have intuition to say whether it's good advice or bad advice. I don't know if I do. But it turns out that if you do that, if you take this advice, and every time that you have the chance of going into a corner or elsewhere, you choose the elsewhere. So you avoid corners. And it turns out if you run the Monte Carlo simulation, and this is a problem, and this rule is followed, you add 2.1 bits of information. So the so-called exogenous information, the difficulty of the problem goes down from 7.4 bits, and you've added 2.1 bits of active information. So the difficulty of the problem now is 5.3 bits. So it's a little over the probability of, it's a little bit over the probability of flipping a coin 5 times and getting all heads. So it improves it quite a bit. I mean, 2 bits is by what, a factor of 4, right? So that's quite a bit. So this is not obvious that there's active information there, but the guy gave you good advice. So another guy comes along, and he says, no, this is really stupid. This is the way it's been done for a long time. But what you want to do is every time that you have a chance, jump into a corner. The other guy, the first guy, was just totally bogus. So you play the game, and every time you have a chance, you always jump into a corner. Well, what happens there? It turns out the second guy doesn't have domain expertise. And this is the challenge again of domain expertise. It has to come from an expert, because if you took the advice of the second guy, you never win. You never win. The endogenous information is minus infinity. Your probability of winning is 0. I'm sorry, not the endogenous, but the active information is minus infinity. You never, ever win. So again, I don't know about you guys, but just looking at this advice, it isn't clear which one is good domain expertise or bad domain expertise. Now, I did it with Monte Carlo simulations. I had a wonderful student, Winston Ewart, who did this using a tree diagram, and he computed it not probabilistically, but deterministically. Because what happens is you have the number of values here, 1 through 12, right? And this is going to be your empty square. And then once you choose this, you have what, 11 more, well, I don't know. I don't know what anyway, the point is he did this by an exhaustive tree search. And he actually built a tree. See, if you do 1, there are only so many. Okay, I kind of screwed it up. If you only have, if 1 is, or no, let's do 1 in the middle. If 3 is true, you only maybe have 2 ways to jump, right? And then depending on here, you might have 3 ways to jump. And so you can see you can build this tree up and literally do an exhaustive deterministic tree. Now the tree is going to be enormous, and you couldn't do this for a really complex problem, but the tree is going to be enormous. And once you get to the end, each one of these labels tells you how many you have left: 3, 1, 2, 2, 1. And you look at the number of cases where there's 1 left, where there's no more jumps, and you take the ratio of that to the other results, and you get about 7.4 bits also. So he computed it deterministically. So if you're into computer programming, and people into computer science know about tree searches and how you can do this sort of thing, you can literally show, not through an approximation, not through a Monte Carlo simulation, but exactly that this was about 7.4 bits. So let's go back to the illustration here and what we're trying to illustrate. The NFL has nothing to do with football. It's the no free lunch theorem has been used to address the sometimes outrageous claims that have been made by specific optimization algorithms. So it does turn out that we have just shown that it is important when you get advice, you better get it from a domain expert and not somebody at random that makes up the advice. Because if somebody is making up the advice, maybe it isn't good. Now, we're going to be talking about training. We mentioned that we could train, for example, the fuzzy tree, or the fuzzy Mamdani control. We could train, for example, for the fuzzy membership functions. Well, it turns out that most training is nothing more than a search algorithm. Neural networks are trained using a search algorithm, and they search for the best solution for a classifier. Here, for example, is a graph of the height versus the weight of sumo wrestlers and basketball players. Okay. And what we would like to do is we would like to build a classifier for these sumo wrestlers versus basketball players. And we are going to build a classifier, and this is our classifier. Is it the best classifier? I don't know, but this is the one that we're going to choose. We're going to choose a point A on this axis, and we're going to choose a point B on this axis, and we're going to connect a line through these points A and B. And then we're going to find out what values of A and B give us the best result. Is that okay? So it's going to be a search algorithm that gives us the most accurate classification of sumos and basketball players. And everything above the line, we're going to say is a sumo wrestler. Everything below the line, we're going to say is a basketball. Okay, quick. Which comes first in the dictionary, baseball or basketball?
Baseball.
Baseball.
Okay, Trevor won the lottery. Okay, very good. Okay, so this is basketball. Okay, because we know basketball people are usually are taller, but we know that sumo wrestlers are, pretty heavy. So all the sumo wrestlers are going to be up here. So we do the search and we look at the number of correct classifications for all values of A and B. And we get this curve here. This is a curve. This is called an exhaustive search, where we have looked at every value of A and B, and we have looked at the number of accurate classifications for different choices of A and B. Does that make sense? So we chose a value of A and B. We counted how many sumo wrestlers were above the line, how many basketball players were below the line, and this is the result that we get. Now, as you can see, there's a nice plateau up here where we get the maximum value, correct? But notice this again is a search over all values of A and B. So what we want to do is we want to choose A and B somewhere in this little plateau here in order to give us the best result. So do you see how the training algorithm is a type of search? And this is an instantiation of one of those. So we have, for example, here we have A is equal to 175 and B is equal to 330. And this gives us the best differentiation. It turns out in this case, the data is cooked a little bit because there are no misclassifications. Often you will have misclassifications. You'll have I don't know, a fat basketball player, or maybe a really skinny sumo wrestler that'll be down here, and you have misclassifications. This is more typical than other things, than the data which I gave you here. But here's the idea of classification. Once you train the classifier and you have your value of A and B, you take all of this data and you throw it away, and you come over here and you say, okay, here is my classifier. And my classifier is such, if you give me any new person and I know it's a sumo wrestler, a basketball player, if it's above the line, I say it's a sumo wrestler. If it's below the line, I say it's a basketball player. So I have taken the data and I have sucked out the essence of the data to come up with this classifier on the right. And again, it's a result of search. It's a result of search. I did an exhaustive search here, but you could also do more eloquent searches. Now notice there was a lot of assumptions that I had in my classifier. Remember this no free lunch theorem. I assumed that I could choose a value here, I could choose a value here, and I could look at all of the results, or all of the classifications. But man, this would not have worked if I had all my sumo wrestlers on the right and all my basketball players on the left, right? This worked because I had played around with my data and I knew there was kind of a bifurcation here. If I had my data as I was shown on the right, and I tried to choose an A and a B, two A's or two B's, one for basketball player, one for the right thing, man, I would not get any good classifier there, would I? I wouldn't get any classifier. So therefore, the assumption and the structure of the classifier is inherent to the solution of the problem. And here's an extreme example. Suppose that, let's see, suppose that I had, okay, no, I have this backwards. Suppose that I had A and B here, and I assumed that basketball players were above the line. Now, before I assumed that sumo wrestlers were above the line, didn't I? And for good reason, it matches. But suppose I was really stupid and I assumed that basketball players were above the line and sumo wrestlers were, let's see, no, this is right, shoot. I assumed just the opposite of what it was, okay? And so everything down here would be a basketball player. Everything up here would be a sumo wrestler. This is terrible because if I do an exhaustive search again for all values of B, assuming the incorrect side that these things are happening on, my plateau comes up here. Before I got a value of 30, this classifier gives me a value of 35. It clearly isn't as good a classifier, and you can see obviously why that's the case here. Okay. So here's a problem I would like you to do. I know you're working on the swarm, and I would like you to look at, much like we looked at the case of the Cracker Barrel puzzle, and I'd like you to do an analysis on tic-tac-toe. Everybody has played tic-tac-toe, right? And let me go. I think I changed some things here. So let me go to the Google Sheets. I think I'm going to have to reshare here. Okay, so let me know if you don't see the Google Sheets. So the project number 3 is, what is the endogenous information for a 3x3 tic-tac-toe on a 2D grid? And by the way, this is a problem I've always wanted to work. It's a simple problem. It's a tractable problem. And instead of me doing it, I want you to do it. Okay. So I want you to evaluate the endogenous information of a 3x3 tic-tac-toe on a 2D grid. Now, first of all, there's some assumptions here. The assumptions are if you go first or the other person goes first. Let's assume on all of this that you go first, except when we get down here. So we'll assume that you always go first. So if you go first and you choose a random X and your opponent goes second and they choose a random 0 and you go back and forth, what's the probability of you winning? That's the probability. And if you take the log minus the log base 2 of that, you get the endogenous information, which is a measure of the difficulty of the game of tic-tac-toe if you have no domain expertise. But you know you do have domain expertise. For example, you should know how to block, right? You see 2 zeros in a row. You want to block that, right? So that the other person doesn't win. Suppose you know how to block and always start with the center square. Everybody that's played tic-tac-toe, every nerd that's played tic-tac-toe a little bit knows the first place that you want to go is in the center square, right? Everybody knows that. So that is your domain expertise. So the question is how many bits of information does that add to your chance of winning if you also know how to block? Or also, what happens with a corner square or with a side square? I suspect, but I don't know, that some of these might be negative active information. You might worsen your chances of winning as opposed to a totally random thing. And then I'd like you to repeat it when your opponent knows how to block. So yeah, so this is the analysis, not of the Cracker Barrel puzzle, but of the much simpler tic-tac-toe problem. Okay. And unlike the Mamdani control, there is no tic-tac-toe MATLAB toolbox. So you're gonna have to do this on your own, I suspect. Okay.
I have a question.
Sure.
Do you want us to do like the Monte Carlo method or deterministic method?
I would leave that up to you. If you have the skill to do the deterministic method, which I confess is beyond my capability, yeah, do the tree. I mean, that would be kind of cool. Does anybody? I'm not committing you, but does anybody think they can do the tree? Matthew can, okay, and Colin can. Yeah, if you can do the tree, that would be kind of interesting. So that would be interesting to compare to the Monte Carlo simulations. And then if you do the Monte Carlo simulations, the question is, how many Monte Carlo simulations which do you have to do? I would do a lot. I would do at least 1 million. And I think you could probably crank that out pretty straightforwardly. And then I would like to see your code, but most interestingly for the class presentation, I'd like to see your results in a table for class. And certainly with this, if you want to talk among yourselves, that's fine. If you want to go solo, that's fine too. Okay, any questions at all? So I give these projects because it forces you to dig deeper into the topic. Mamdani control made you dig deeper into the idea of fuzzy control. Did everybody see Innocent? He just went inside Pat Neff Hall. Let's see if he came out of Pat Neff Hall. Okay. Welcome back. You were there visiting President Livingstone, I assume, right? So I forgot what I was saying. It might have been, the reason for doing it. So hopefully the swarm will give you a better idea of simple rules giving result to very interesting emergent properties. And I'm just reading a book now called Algorithms in Animals. And it includes some things about social insects and homing instincts and different things, and how we have these algorithms and where these algorithms came from. It's a very, very interesting book. And then this is going to make you think more deeply about the idea of endogenous and active information, because it's a hands-on sort of experiment. Okay. Any questions at all? Okay, if not, I want to talk about, I want to spend a little bit of time on artificial neural networks. That used to be, you can see in the back, this is really interesting. Russ Reed and I wrote this book, Neural Smithing, a long time ago. Gosh, it's been decades, I think. And it's still a very popular book. And if you look on Google Scholar, it was referenced more times last year than it was any year previous. So this contains some ground truth that is applicable even today. So I think that I gave you a link to the book on, did I give you a link to that? Let me look. Okay, it looks like I didn't. I will give you a link to that book in a PDF format so that you can have it. And many of the slides that I'll be using come from that. Now, one of the things about teaching about neural networks is that neural networks appear elsewhere in the curriculum here at Baylor University. Some of you have taken Professor Dong's class in artificial neural networks, dedicated heavily to neural networks, and also to Professor Pablo Rivas's course in computer science in terms of neural networks. Both of them go much more deeply into the things that I'm going to talk about, but we're going to kind of skim the surface, give you an idea of what artificial neural networks to do, the methodology behind them. And I'm also always very interested in the history. It turns out that history is something which unfortunately is lost. I just saw a news article where one of the brilliant neural network researchers, Geoffrey Hinton, was pointed out as one that invented the algorithm of error backpropagation, which is used to train most of the neural networks today. And there was he was confronted with the idea, and he says, "No, I didn't write error backpropagation." So there's lots of misinformed news out here as people have a short-term memory into the historicity of what's happening. That's a reason in the beginning of the course, we talked about Bernie Woodrow and some of his pioneering work and the fact that he was doing in the 60s what a lot of people are doing now and saying it's really, really great. Now, clearly Bernie Woodrow's neural networks were nowhere as sophisticated, nor the results were as impressive as they are today. But the same principles were applied then as now, which is, I don't know, I find fascinating. And I think it's important for a number of reasons to maintain those historical roots. So with that, let me talk about neural networks. I have a short sort of introduction to it, and then we will, and then I'll talk very briefly about some of the modern neural networks, the GAN, generative adversarial neural networks, and the deep convolutional neural networks. And I tell you, the deep convolutional neural networks were an act of genius, and we'll see why as we get more deeply into what happens. But again, I'm not going to spend the time. And if you're interested more in the details of what goes on in neural networks, you should take either Dr. Rivas's class or Dr. Dong's class. Has anybody taken that class or is planning on taking it? Okay.
Currently in it.
Oh, you're in it?
I'm in Dr. Dong's class, yeah.
Dr. Dong's class. I understand his class is very project oriented. Is that right?
Yes.
Okay. And would you like me to go over some of the tools that are available? Because it does turn out that, but let's see, what is there? There's TensorFlow and PyTorch and all of these incredible neural network training algorithms that are available for free if you want them. And a lot of people are doing a lot of very strange and interesting things. You might have heard of deep fakes, right? Well, we talked about deep fakes, for example, this person does not exist, .com, and other ones that generate deep fakes, both in still images and in videos. And that's done with a neural network, with a generative adversarial neural network. And We'll talk about those just a little bit. But again, I don't want to spend a lot of time on that because of the availability of Dr. Rivas's course and Dr. Dong's course in the area of neural networks. So, okay, let's see, are you seeing my slides? Yes, you are. You're seeing my slides. If you're not, holler and let me know. First of all, artificial neural networks of the type we're going to talk about is associated with labeled data. It's labeled in the sense that if you have, say, a picture of a duck, there's this little subscript that says this is a duck. If you have another picture of a dog, it says this is a dog. So every picture is labeled with some sort of descriptor so that we can know what it means a priori. There's also unsupervised learning. Unsupervised learning is where you are given data which doesn't have labels associated with it then. And in many cases, well, I think a lot of natural language processing is based on this. And there you need to use algorithms which are referred to as clustering algorithms. Then there are also reinforcement learning. Reinforcement learning doesn't necessarily, in its purest form, doesn't use labeled data or unlabeled data. Rather, it looks at a problem. And you can look at a problem, for example, like the rules of chess. Now, the rules of chess are there, they're fixed, there's no data associated with them. But the question is, can you train artificial intelligence to follow the best rules in order to win at chess, like Deep Blue did with Kasparov, or that OpenAI did with Lee Sedol in the game of Go. Go is a similar board game. There's lots of rules, but there really is no data. But the question is what is the best way to apply those rules in order to win this game, which is laid out very nicely. And some of the things that have happened with the reinforcement learning are just astonishing. One that really astonished me was that neural networks were reinforcement learning was applied to win at Texas Hold'em. Now, if you had asked me prior to hearing and seeing the results of Texas Hold'em, I would say that poker is largely a game of chance, of bluffing, of psychology. Do you agree with that? But apparently it's something which could be mastered. And this adversarial neural network was able to beat world champions at Texas Hold'em. And the interesting thing in these World Series of poker, the same people seem to show up again and again. So there is some degree of skill there. So the neural network was able to get more degrees of skill. But we're going to look specifically at supervised models where you have data and this data is labeled. So what you're given is an input, a stimulus, and then you get an output, which is a response. The output is the label. So if you input a picture of a dog, the output is going to be dog. And the object is to train a machine to simulate the input-output relationship. This always reminds me of, okay, I'm going to ask a question. I think I know the answer. Has anybody ever here seen the movie Invasion of the Body Snatchers? No one has seen Invasion. Has anybody ever seen the movie The Stepford Wives? No. Okay. Well, I want to explain the Invasion of the Body Snatchers. There were these pods from outer space that came to Earth. It's a great movie, by the way. And the 1950s version was redone many decades later, but the 1950s version really stands up well. So these pods came down. And when you laid beside a pod and went to sleep, that pod took up on all your features. Okay, it took on your, it took on some sort of modicum of your personality. It took on your physical shape and everything else. And then it devoured you. You ended up dead. And then the pod person got up and interacted. And people that weren't really familiar with the pod person thought, you know, this is a guy I know. This is the same guy. They had no reason to suspect that it was an imposter. But people who were close to the person said, you know, this isn't Uncle John. Something's wrong with Uncle John. And so this, by the way, is characteristic of most of the artificial intelligence that you see, that Some of it can come out and say, whoa, this is really impressive. But if you talk to a domain expert in the area that the neural network is trying to do something, you'll see that these experts come along and they say, well, you know, this is a cheap imitation of what humans can do if you had domain expertise. So here's my point. Imagine the human body as a set of data. Now, this data has a source, and we don't know what the source is. There's no equation for it. There's just a source of data. And you lay a neural network, the pod beside this data, and the pod begins to reconfigure itself in order to simulate the input-output data result here. So it's kind of taking the input-output data that you have, and it's generating a system which duplicates or simulates that input-output, just like the pod was copying the original person. And so that's the idea of the neural network. So the object, as you see here, is to train a machine to simulate the input-output relationship. And there's a bunch of different types. You can have classification. Classification would be, for example, if you wanted to differentiate between cats and dogs and alligators, you would train a neural network to differentiate between cats and dogs and alligators. So if you're given an input, it would designate it was a cat or a dog or an alligator. It would give you the class. There's also regression. An example of regression is if I were trying to forecast the power load for tomorrow from the current data today. Most of the power companies in the United States use neural networks to do exactly that. They like to forecast the power load for tomorrow as a function of a number of variables: the day of the week, the forecasted temperature, the current temperature, the power use of today. And they like to do this because on the grid, if you don't generate enough power, you have to buy it from the free market on the grid. And if you generate it too much, you have to sell it on the market. And you don't want that uncertainty of whatever the market is demanding. So here, the output is not dog, cat, alligator. The output, if you will, is a floating point number or a floating point time series, if you will. So this is an example of regression. So classification is discrete outputs versus regression, which is continuous outputs. So here is, this is an old, let me ask you this. Anybody know who this is? This also shows my age. No, okay. That's Paul Harvey. Does anybody recognize the name? Probably not. Okay, who is this? That's James Arness, Matt Dillon from Gunsmoke. And we'll see, this is more in the recent past. Who's this? Wow. That's Rush Limbaugh, just passed away last year. And you guys better get this one.
Reagan.
Ronald Reagan, good for you. Okay, he's not too far gone in the past. He's further than the past than Rush Limbaugh was. Limbaugh died of lung cancer recently. Anyway, here's the basic idea. This is me as a younger me. This is me as a younger me before, back when I used to dye my beard. I gave up on dyeing my beard and it just came out white. So if you give this to a classifier and it says it's a marks and you do not marks, not marks, not marks, marks, and not marks, and you train the classifier on hundreds and thousands of different pictures of me, hopefully you would get a classifier, and the classifier given a picture of me would say that it was marks. That's what you would like to do. The test image does not appear in the training data. In other words, we'll talk about this a little bit, but it turns out that this is not in the training data. This image is not in the training data. The classifier has not seen this image before. And that's very important. That's the difference between learning and memorization. If we simply were looking at a tally of a number of different training data, and we're trying to memorize and get the closest image, well, we could do that with a table lookup. But what we would like to do is we would like to have that classifier recognize the picture that it hasn't seen before. That's learning. if you can only recognize things which you've memorized in the past, then that isn't learning, that's memorization. So here is the idea. This is a geometrical interpretation. We have, for example, a set, and you could think of this in some sort of Euclidean space. And we have a number of pictures, and here's a picture, here's a picture, here's a picture, here's a picture. It's like sumo wrestlers and basketball players, except this is marks and not marks. So we have all of these Marxes here, and then out here we have all of these non-Marxes. Now there is a truth. We can assume that there's maybe an underlying truth between Marxes and not Marxes, and that's given by the white line here. This is represented by the concept. Usually what happens when you train a neural network is it gives you a representation. That representation is hopefully close to the concept and can truly differentiate between Marxes and non-Marxes. And so our job is to get kind of this representation closest in some sense to the truth. Here are some examples. I mentioned load forecasting, and where the input is the temperatures, the current load, the day of the week, whether it's a holiday or not. I did a lot of work on load forecasting with neural networks, and we had some fascinating results. One was the Thanksgiving effect, which the power consumption would go along until about 11 a.m. when there was a big spike in the electrical demand. And we finally figured out that that was everybody turning on their stoves to cook their turkeys, literally. So that was an anomaly, and unfortunately was something that you couldn't forecast. You just didn't have enough information. And so you input, so the training was historical data, and that's the cool part about problems of this sort, is that you have a lot of historical data that you can call upon. And then the test is you put in the same sort of data that you were trained with, and it will give you the output for tomorrow. So this is a classic example of using neural network for classifying. Now, what do you want out of a classifier? You want good accuracy outside the training data. You want to not memorize, but you want to learn. A good classifier has an explanation facility. This is one of the big obstacles of the application of neural networks. If it gives you an output, if a neural network says your input is a cat, it'd be nice if you could know why it was recognized as a cat. And neural networks are known as black boxes, and that's not that good of a result. Everybody wants explanation facilities, and there is lots of work. In fact, there's been lots of work happening on this for the last 3 or 4 decades, trying to get good explanation facilities for neural networks. You want fast training and fast testing. And this also doesn't apply to neural networks, especially very complicated neural networks. Even deep convolutional neural networks with gobs and gobs of hidden layers can take, days to train, if you will. And here are some classifiers and regression machines. Neural networks are not the only one. There's classification out of regression trees, nearest neighbor lookup, vector support machines. And then if you have neural networks, there's a whole smorgasbord of different types of neural networks. And these are a few of them. And I think that we'll probably stop here, and we'll talk about next time the model of a neural network and what we can do in order to characterize the neural network. By the way, the error backpropagation algorithm, which we talked about, Jeffrey Hinton, was indeed invented by a guy named Paul Werbos in 1975 in his PhD dissertation at Harvard. And I recently did an interview with Paul Werbos. He's still alive and kicking and doing great and wonderful things. And I'm going to invite you to listen to that podcast and listen to the man that came up with the idea of error backpropagation. One of the things that I'm always interested in is when people come up with great ideas, where did those ideas come from? You know, I believe that most creativity has a flash of genius associated with it. And we talked to Paul about that, and you'll be able to listen to that when I put that up. Okay. Any questions at all? We're out of time. Okay, if not, I think that we are finished. Thank you, gentlemen. We're all male. And we will see you soon. Take care.